Appreciate you coming out today. I'm Stan Cole. I'm head of the Aeroelasticity branch. Many of you I recognize out there, so a lot of you know me. But I'm going to take just a moment to introduce Bob to you also. You can see from his chart here that his name is Robert V. Doggett Jr., but he goes by Bob. And a lot of you also know Bob, but maybe you don't know very much about his career, and so I'm going to cover just a few things before he talks today. First of all, he's a native of Richmond, Virginia. Came to work at NACA's Langley laboratory immediately following his graduation from Randolph-Macon back in 1957. He was initially assigned to Charlie Watkins' analysis section in the Dynamic Loads Division, but he never actually worked there. By a happenstance that Bob describes himself as good fortune, he ended up going to work in Joe Martin's Flutter project section, and there he began to work with aeroelasticity, even though at the time he didn't really know what that meant. And probably a lot of us that have worked in the field can say something similar to that in terms of the beginnings of our career. His initial work involved Flutter model testing in a number of different wind tunnels and also some analytical studies. Work ranged from simple research studies to more complex investigations of full-scale designs. In January of '62, he was reassigned to the newly formed Aeroelasticity branch, which was still in the Dynamic Loads Division. And this began his association with the Transonic Dynamics Tunnel that he will talk to you about today. And this was a relationship that either directly or indirectly remained there throughout his career, his relationship with the TDT. At the time of this transfer, the focus of his work was shifting away from airplanes and toward launch vehicles. And Bob's fairly renowned in that area with regard to Buffett work that he's done for launch vehicles as well as for fixed-wing aircraft also. From that point on, though, he was pretty much involved in a hybrid mix of anything that flies. And Bob's been very influential with regard to experimental studies as well as impacting what was done with analysis studies throughout the years in aeroelasticity. And few people have the breadth of aeroelastic research experiences that he has. While in the aeroelasticity branch, he served as head of the Flutter section, then became leader of the Flutter group. And this was after Don Harris got rid of section heads in the research organizations in 1977. And then in January 1981, he began a 7-year tenure as head of the Configuration Aeroelasticity branch, formerly the Aeroelasticity branch, and now currently, after dividing into several different aeroelasticity branches in that time period, is recombined in today's aeroelasticity branch again. At this point, I'd just like to say, and Bob, I've shared this with Bob in the past, but only with Bob, and I've never said it in public, but I came into the aeroelasticity branch not too long after he became a branch head. I co-opted before he was branch head in 1980, and then I came in 1982 as a permanent employee. And Bob Doggett is very much, as I have worded in the past, the father of my career. And so I have a special relationship with both him and the TDT, and very much appreciate what he's contributed to my career. In 1988, he spent a brief period as chief scientist of the Loads and Aeroelasticity Division, and then for about a year as chief scientist of the Structural Dynamics Division until he became assistant chief of that division in July of 1989. In October 1994, he became special assistant to the chief of the Structures Division. He retired in March of 1995, and for the last several years has continued to work with the Aeroelasticity branch as a distinguished research associate, primarily serving as an archivist for our Aeroelasticity archive, our library, and that also is very much appreciated in terms of his continued contribution. He's published many technical papers, made many technical presentations. He is actually co-holder of 2 patents that resulted from his research. And as I've already said, he's known throughout the world for his contributions to aeroelasticity. His accomplishments were recognized by a number of group and individual awards throughout the years, including the NASA Exceptional Service Medal and the Director's Award from the Army's Aerostructures Directorate. And I should have started probably with just a word about this presentation. He made this presentation to the Aerospace Flutter and Dynamics Council, as is stated here, just a few weeks ago, I guess. And that was both the presentation and the council meeting here at Langley was planned to be held in conjunction with the 50th celebration of the TDT. And a number of folks were quite impressed with the information that he brought in this presentation. And so not only is he presenting it to you today, but we're also trying to capture this on video today so that we'll sort of have the story, if you will. So with that, Bob.
Well, I appreciate y'all coming today. I see a lot of people have familiar faces, but since this is going to be videotaped for posterity, I thought we might step back a little bit and talk about aeroelasticity. When I gave this talk initially for the Aerospace Flutter and Dynamics Council, I was speaking to friendlies, and they knew what I was talking about. They knew what aeroelasticity was and that sort of thing. But perhaps there's somebody here that doesn't know, but when perhaps somebody look at the videotape in the future, they might not know either. I don't know. This is high tech for me. I'm a more physical pointer guy. Aeroelasticity exists because flight vehicles are flexible. There's a reciprocal relationship between load and deformation. Take an airplane wing, as it flies along, it will deform due to the aerodynamic load. The new shape will change the load, and eventually some type of equilibrium condition will be reached, or an instability will occur. There are three types of forces that are involved in aeroelastic phenomena. They're the structural inertia, elastic, and aerodynamic forces. Strength doesn't have anything to do with any of this stuff we're talking about. It's stiffness. And how these three forces combine, how these three forces combine together determine whether it's going to be a static phenomena or a dynamic phenomena. If the elastic forces and the aero forces combine, then it'll be a static phenomenon. An example of a static phenomena is aileron reversal. In other words, the shape of the wing will change such that the ailerons act in the opposite sense. So when the pilot wants to roll to the right, the plane goes to the left. There was a famous airplane that had a problem with that, and that was the Japanese Zero during the Second World War. It didn't suffer from aileron reversal 100%, but it suffered from a big loss in aileron effectiveness. And the tactic was to get it into a high-speed dive and then pull away. If a Zero was on your tail, then he couldn't turn as fast as you. And he tried to roll, he couldn't roll as well as the American planes. Dynamic phenomena is something like flutter. Flutter is a vibratory thing, a combination of all three of these forces. Aeroelasticity is perceived as evil. It's not a good thing. It can't be allowed to happen. You can't let airplane wings flutter. You can't let airplanes have aileron reversal. You can't let the buffeting be too severe. So these things have to be designed out of airplanes. If an airplane or a helicopter or a launch vehicle or whatever it may be has an aeroelastic phenomena, to fix it generally you have to add stiffness. When you add stiffness, you add weight or mass. When you add weight or mass, you penalize the performance of the vehicle in one way or another. Less payload, more fuel consumption, shorter range, or whatever. Now, it's not always evil. Whoops. It's going to take me a while to get used to this, I think. The Wright brothers used aeroelastic principles in the lateral control of their flyer by changing the shape of the wings, put on those cables. They didn't know, the word aeroelasticity hadn't been coined. It wasn't coined until the 1930s by the British. Recently, there's been a lot of work focusing on how can we use these deformations in a good way. So maybe aeroelasticity is becoming less evil, but it's perceived generally to be bad. Okay, as Stan mentioned, I initially gave this presentation to the Aerospace Flutter and Dynamics Council several weeks ago. And what I'm going to be talking about is how the TDT came into being. And what I'm going to do is I'm going to talk about how the original notion arose, and I'm going to follow the story through the selling of the idea, how funding was acquired, design and construction, and some bumps along the road. And there were some big bumps along the road, and then leading to the finished product. And also I'll mention some related events that might be of some interest to you. From the 1930s through the 40s, aeronautics and airplanes had changed quite a bit. They'd gone from these relatively simple configurations such as B-17 that were very stiff vehicles. You could look at the aeroelastic characteristics of the wing independent of the aeroelastic characteristics of the tail. In other words, you didn't have to look at the whole airplane. You could look at the various components. And also these babies operate at relatively low speeds, essentially incompressible flight speeds. Things that evolved from the B-17 to the airplane like this B-47. It's a lot bigger, swept wings, heavy engines mounted on pylons down below and forward of the wing, very flexible, so you can't isolate the wing from the tail. You have to look at the structural dynamic characteristics and the aeroelastic characteristics of the whole airplane. And furthermore, these babies were operating at transonic speeds where compressibility effects were important. So there's a question on the minds of aeroelasticians, both in the airplane companies and also in the government laboratories, is how do we predict the aeroelastic characteristics of these new complex, very flexible configurations operating at transonic speeds? Berkeley Kinnaman, who was head of the loads group at Boeing and also had been heavily involved in determining the aeroelastic characteristics of the B-47, said this was a very difficult task and perhaps even impossible. Well, this question received a lot of, developing an answer to this question received a lot of emphasis here at Langley. A fellow by the name of Arthur Regier really took upon himself to find out the answer. Regier was the head of the vibration and flutter branch in I.E. Garrick's Dynamic Loads Division. The Dynamic Loads Division, we're talking about like 1950, 51 time period here, was a relatively new division that essentially had been created by renaming Richard Rohde's Aircraft Loads Division and combining it with the flutter and acoustic people who had been in the Physical Research Division. The Physical Research Division had once been headed by Theodore Theodorson. You aeroelasticians know who Theodore Theodorson was. Non-aeroelasticians, it's just an interesting name. Regier conducted informal discussions with his colleagues in the Dynamic Loads Division, also with other research divisions around the center. But really, the vibration and flutter branch at this time was the seat of aeroelasticity knowledge here at Langley. But that division also did some work with some of the other divisions. In other words, Pilotless Aircraft Research Division fired off little rockets with flutter models attached on them, and the flutter information would be telemetred back to the ground. Also, Regier had a lot of contact with his industry counterparts, particularly the people at Boeing. And also, Regier was a pretty astute guy. He was smart enough to keep his management in the loop about what he was thinking about. And also management, not here at Langley, but buddies like Rohde, who now, the former head of the Aircraft Loads Division, who was now one of the assistant directors for research in Washington headquarters. Regier finally thought he had an answer. The answer is a new wind tunnel. That's not surprising, is it? We're talking about doing something at speed ranges where theory doesn't work. And also, Langley at this time was a wind tunnel place. Got a problem? Let's run a wind tunnel test. This wind tunnel had to operate from subsonic through the transonic speed range. Transonic wind tunnels were relatively new. There was only 2 or 3 in existence here at Langley at this time, and they were almost brand new. Test section had to be big, at least 16 feet, preferably 20 feet. That's because you wanted to test full span models of these big airplanes. Operate from near vacuum to above atmospheric pressure, and use air and freon as a test medium. Freon has a lot of advantages for aeroelastic testing. First of all, the speed of sound is about half that of air. Its mass is density is 4 times that of air, which means it's easier to design and fabricate dynamically scaled aeroelastic models of actual flight vehicles. Also, the lower speed of sound means things happen half as fast. Model frequencies have to be half in freon as compared to what they are in air. Have a helicopter that only has to go around half as fast in freon as it does in air. Also, there's some economic advantages. For a given dynamic pressure and Mach number, it takes considerably less electric power to power a Freon tunnel than an air tunnel. And also there's a Reynolds number effect. You get about 2.5 times the Reynolds number in Freon as you do in air for the same dynamic pressure and Mach number. Regeer liked the Mach number 1.3, and this baby is going to have some special features that particularly are tuned to aeroelastic testing. Aeroelastic testing is a risky business. Models can be easily damaged, blow down the tunnel. So you need some means of stopping the tunnel quickly when one of these things occurs. So a flutter point is reached, slow the tunnel down so the model doesn't vibrate to destruction. But even though you can slow the tunnel down, it doesn't always work. Sometimes the debris goes down the tunnel, so you need a lot of protection for your fan, something that's not ordinarily in most wind tunnels. Also want good visibility. Aeroelastic phenomena, as most of you know, are events. And the test people need to see that event has occurred. It's not like measuring pressure data where you just go out and gather a whole slew of data and then analyze it later. You've got to be able to see your model and tell what it's up to. Also, you need a lot of illumination so you can do high-speed photography. So Regeer's got the answer, but he doesn't have any wind tunnel, he doesn't have any money, doesn't really know how to go about doing it. But he really has two options: build a brand new facility or modify an existing facility. Regeer even has an idea of what facility here at Langley we can modify. Doesn't belong to him, belongs to the full-scale research division. And that's a 19-foot pressure tunnel. 19-foot pressure looks a lot like the TDT, if you're familiar with what the TDT looks like. 19-foot pressure tunnel was built and opened in the summer of 1939. It was the first attempt to combine large size, high pressure into a single facility to achieve high Reynolds number. The technology pretty much had passed this facility by. It was perceived as a super propeller research tunnel for one thing, but its 300 mile an hour top speed pretty much limited its usefulness. Some interesting tests and important studies were conducted there during the Second World War, but no research of any significance had really come out of this tunnel. And it was kind of a white elephant. So Regeer says, why don't we modify it if we can't build a new? So he goes over and talks to the people in technical services. Technical services is the engineering part at this time. I don't know what it's called now. I'm sure it's some grandiose name. But this is where the engineers and that sort of thing, the people that design stuff, lived. He went over there and approached them with the notion, could they come up with some kind of cost estimates for either building a new tunnel or modifying the 19-foot pressure tunnel? Well, that was really such a stupid question to ask these people, because at this point in history, NACA Langley probably had as good a wind tunnel design capability, if not better than any place else in the country, and certainly on a par with anything else in the world. So he was asking a bunch of experts for their opinion. Well, remember, his test section was 16 by 20. They have to pick something. They couldn't design and cost out something, well, 16 feet by 20 feet, make it out of elasticity. So they picked 16 foot because that's what they thought would be the maximum size you could fit in the 60-foot diameter plumb of the existing 19-foot pressure tunnel. Also, the pressure range, would take maybe 100,000 horsepower or so to get Mach number 1.2, 1.3 at 2 atmospheres of Freon. So the pressure range had to be reduced. So they said, okay, we can have a tunnel that would test above atmospheric pressure in the lower Mach numbers, but at the higher Mach numbers, we're going to have to test below atmospheric pressure. And although Regeer liked 1.2, they said, well, 1.3, they said 1.2 is probably about as high as we can go, because there's a big difference in horsepower requirements in going from 1.3 to 1.2 or 1.2 to 1.3. So they took these revised specifications and came up with some cost estimates. Build a new facility would cost $15 million. That's a lot of money even today, I guess. Or to modify the existing 19-foot pressure tunnel, it's going to cost $9 million. Of course, Regeer don't have any money, But he certainly can approach people, his management here at Langley, his friends in headquarters, and see what kind of reception he might get for these two figures. Well, for the $15 million, the receptions he got, forget it, buddy. There's no way you're going to get $15 million to do this job, no matter how great it is, how important it is. But there is a possibility of getting $9 million. Okay, so as far as Regier is concerned, modify the 19-foot pressure tunnel for $9 million. Wonderful. But he didn't have $9 million. He hadn't sold the project yet. But before we talk about selling the project, let's see what really we're talking about in modifying the 19-foot pressure tunnel. The whole notion, keeping the cost down, and a lot of the difference between the $9 million and $15 million was just in the tunnel, the tunnel shell. The idea was that you use the existing 19-foot shell. You have to add some stiffening because it's going to be operating below atmospheric pressure, where the 19-foot tunnel just operating above atmospheric pressure. Slap in a new transonic test section, new motor. The motor would be in a separate building outside the tunnel. A shaft would go through the tunnel wall to the rotor in the cell in this back leg. You have to add an internal cooling system. The existing 19-foot tunnel with its 8,000 horsepower motor was externally cooled, but the 30,000 horsepower new motor will have to have some internal cooling, so there'd be cooling coils added in this ring here and a cooling tower added in this courtyard here. And since we're going to have a Freon system, we need a Freon equipment, right? So we're going to send this building over here 2 stories, and that's where the Freon system is going to go. So sounds pretty simple. 4 or 5 little things: new test section, cooling tower, more powerful motor, Freonization system, and away you go. But before this can happen, somebody's got to come up with the money. Regier, even though he saw the merit in a transonic tunnel, Regier was a supersonic guy. He thought the transonic problems were near-term, the long-term problems were going to be supersonic. Now, that may sound kind of naive looking back now 60 years later, but a lot of people shared that same view. So in the spring of 1951, Regier said, if we're going to make this thing happen, we need to make it happen now. Now, of course, means 2 or 3 years. You just don't build a wind tunnel in 2 or 3 in a year or so. And he was even concerned if it could be done in 3 years, the thing might be obsolete. So he goes over and talks to Tommy Thompson, who was the director of research at Langley. Thompson was the number 2 man. He would later on get the title of associate director. And he was the kind of guy that ran the center on a day-to-day basis. So Regier goes over to talk to Thompson, explains what he wants to do. Of course, this is not all new to Thompson, because Regier's been keeping people up to speed on kind of what is going on. But this is the first time he's really laying out a proposal on Thompson's desk. Thompson said, "Sounds a pretty good idea, but we got a big problem here. The full-scale, the 19-foot tunnel doesn't belong to you. It belongs to the full-scale research division. So you've got to get some of those boys on board before we can really talk about doing something like that." So Regier comes back to his office, writes a couple of memos. One memo where he's addressing transonic flutter testing. At this point in history, there hadn't been a single flutter point obtained in a transonic wind tunnel. The transonic wind tunnel is just brand new. So he writes a memo, some of the concerns about flutter testing in transonic tunnels, because it's never been done before. And also writes another memo, the justification of converting the 19-foot pressure tunnel into a tunnel used exclusively for air elasticity research. He takes his memos and goes over to a meeting with Sam Katzoff, who's assistant chief of the full-scale research division. Katzoff was kind of an interesting character. He actually wore 3 hats. He was assistant division chief. He was head of the low-speed tunnels branch. The 19-foot tunnel was part of that branch. The full-scale tunnel was one other tunnel in that branch. Also was head of the full-scale analysis section. So he was a section head, branch head, and assistant division chief. Very influential guy, brilliant guy, and scary to people that didn't know him very well, like me. Also at this meeting was Jim McHugh, who was the head of the 19-foot pressure tunnel section. Gear goes over, takes his memos, lays them out, makes his arguments. McHugh doesn't think much of this idea. I mean, he knows this tunnel is not the greatest thing since sliced bread, but he feels like, we're doing kind of good work. And I don't want to become an aerolastician. I know nobody on my staff wants to become an aerolastician. Kassoff looks at it from a little bit higher up the management chain. He sees this dinosaur 19-foot pressure tunnel, has a chance to maybe make it into something useful and save it. So he thinks Regeer's idea has a lot of merit. And another thing is, Regeer's not trying to steal his tunnel. Regeer didn't want it. He didn't want it transferred to his division. He just wants it converted for this good purpose. So Kassoff goes up and talks to his boss, who was Gene Draley, a relatively new division chief. He succeeded Clinton Dearborn, who had moved up to headquarters as an assistant for management, I think, to Hugh Dryden, the director of NAC at the time. Kassoff goes over and talks to his division chief, who, like I said, was Gene Draley. Draley thinks, hey, this is really good. We can salvage this wind tunnel, do something good with it, and here again, nobody's trying to steal it from us. So Draley goes up to talk to his boss, John Stack. I don't know if any of you know Stack or know him by reputation or whatever, but Stack was a dynamic guy. I mean dynamic with a capital D. Man, Stack thought this was a great idea for a couple of reasons. One, three reasons actually. Save the 19-foot tunnel from extinction probably. Make it into something that would have a worthwhile purpose, and that would be good for industry and the military. NAC was always attuned to trying to have good relations with the industry and the military. And third, Stack was Mr. Transonic Tunnel. He was the guy that recognized the merit of Ray Wright's slotted wall research and brought it into the Transonic Tunnel. So this would be another Transonic Tunnel for Langley. So Stack is on board. And when Stack got on board something, the ship usually left the dock. So he goes over and talks to Thompson and Reed, who was Thompson's boss, the center director. And they agree with Stack. This sounds like a good idea. While all this is going on, there's talk back and forth between Langley and headquarters. I mean, they're not going to fire off a request for $9 million without some kind of preliminary work being done. They have a couple of friends up there, Rhodey and Dearborn. So they've got some who are going to side with this thing. So they fire off what's called an RFA. That's a request for authorization to Washington headquarters. It gets up there on the 29th of June. It has to be there by July the 1st. Well, these RFAs are not very long documents. They're just 2 or 3 pages. And all the spade work had been done. The hard work is getting cost estimates and the justification. Regeer had already written the justification. Technical services already gotten the cost data. So it's just a case of somebody putting together a 2 or 3 page write-up and firing this thing up. This is going to be a fiscal year 1953 project. This would mean it would start, the funding would become available July the 1st, 1952. Headquarters approves this baby. They for some reason, knocked $5,000 off of the request. Now, all I can figure is that they were trying to make some total number come out even. So instead of $9 million, they say, hey, fellas, you can have $8,995,000. Langley's happy. Sounds great. How are we going to do this job? Well, Langley's going to do it just like they have historically done the acquisition of all new major facilities. It's going to be a joint venture between the research owner and the technical services, who will be the implementer. The 19-foot pressure tunnel, from an administrative point of view, would still be the owner of the facility. There'd be a research program project manager appointed. In this case, it was a guy by the name of Bill Connor. Now, I don't know what they saw in Connor's background. Connor was a journeyman guy who'd come here in the 40s during the war. He was a sound researcher, but he just turned out to be a fantastic person. You couldn't have found a better person. So somebody must have recognized something in his background. And what Connor and company were going to be were responsible for is what was called the aerodynamic design. The aerodynamic design is essentially the internal lines of the tunnel. In other words, what's the test section going to look like? What's the slot configuration? How are we going to transition from the existing built settling chamber into the test section? How are we going to transition into the diffuser, the nacelle, that sort of thing? The methodology was going to be, let's say, some experts interested in slots. We got the slot expert here at Langley, and Ray Wright. We'll get his opinion. And I'll give you another example in a minute. We do a lot of analysis and also do some model tests. They built a small model of the entrance cone test section in the first part of the diffuser. I'll show you a picture of that in a minute. But I'll give you an example of one of the expert opinion. Connor was interested in calculating or determining the shape of the nacelle. At this point in time, the nacelle would handle the rotor to which the fan blades would be attached. If you guys are familiar with, you guys and girls familiar with wind tunnels, there'd be the blades, the blade boxes, and then blade boxes would be attached to the rotor. So Connor goes over and talks to Sam Katzoff, who's a resident expert on a lot of things aerodynamic. Katzoff tells Connor, that's not any theories that are going to work, give you any reliable data. And so Katzoff takes a piece of paper and draws the shape on the paper, and he says, this will work. And that's how the geometry of the nacelle was determined. They verified that by some wind tunnel tests later on, but Katzoff just drew it. And everybody had enough respect for Katzoff and his wisdom that they accepted it. This next chart shows a picture of the small model. It's laying on its side. And the top of it, this is the bottom of the test section. This is the top of the test section. Here's the entrance to the test section. The diffuser section is not shown here. Really, a whole lot didn't come out of the model test other than validating the analysis. The only information that came out, not only, but some of the information that came out, was there was some hinge moments measured on the re-entry flaps, which couldn't be calculated very accurately. It's all they're like control surfaces, and all you active control guys know, right? It's tough to calculate the aerodynamics of control surfaces. We talked earlier about the idea of slowing the tunnel down. Connor was the guy that came up with the idea for the bypass valves. And they used a small model to see if that made models of the bypass valves. There's only two. The tunnel only came with two. There are four over that now, but only came with two to see if those things would work. So that's one very useful thing that came out of the model. The aerodynamic design went on. It was completed in the spring of 1954. And it pretty much proceeded independently of some of the other things I'm going to be talking about in a minute, where some hiccups were involved. But one thing that came out of the aerodynamic design, hey, we can't use this part of this tunnel as is. We've got to stick a 34-foot long extension in the diffuser to keep the flow from separating in the diffuser. That's something that hadn't been planned. That's not in the $9 million cost estimate. It's not in any other cost estimates that have been made. So it needs some more money, it seems like. But some guy, I don't know who he is, who he was, remember the motor was going to be in a separate building out here, and a long shaft running through the tunnel wall to a rotor mounted in the nacelle, realized that, hey, if we mount the motor inside the nacelle, as it is with the 19-foot pressure tunnel, don't build this building, don't have this extra long shaft and all, the amount of money we'll save from doing that will offset the additional costs of removing this stuff and adding the insert. So that was good news. Back to the plan of action. The technical services were going to be the implementer of this thing. They're the ones that were going to make it happen. And first thing they were going to do, divide the job up to a bunch of tasks. And we saw on the picture I showed the 19-foot pressure tunnel with the little box on the side. what the main tasks were: new motor, frenization system, and that sort of thing. And also there's some miscellaneous things like new parking lot, relocating the Air Force building, sunshade, modifications to the substation, getting heavier wires, heavier, whatever you call those big cables that carry high voltage electricity from the substation to the new 30,000 horsepower motor. So that was in the miscellaneous. Technical service was to develop a set of drawings and specifications for each one of these tasks and then put it out for bid. Now the drawings and specifications, how detailed they were would depend on the job. For the motor, they would just specify, hey, it's got to fit into this thing and has to have these kind of capabilities. Some of the other stuff, they would actually design what was needed, and they would sometimes ask the contractor, give him a set of drawings, hey, what do you charge me to build this? So there's a lot of in-house design. There'd be a separate contract for each one of these things, put out a competitive bid, and technical services would take care of monitoring the construction with the the research people looking over their shoulder. Everything looked great, but then ill wind came from the north. Washington headquarters redefined what $9 million really means. $9 million actually only means $7.8 million. What they want to do, and what they're going to do, is they're going to cap this project at $9 million, recognizing that they're going to be cost overruns, but they can't exceed the $9 million. So we got to start down here at some low number and work up to the $9 million maybe. A couple of reasons for that. There were a lot of pressures on the construction of facilities budget at that time. And also the NAC was under a lot of flack from certain congressmen about how they handle their construction of facilities activities. They were going to put a cost escalation clause in each contract which would provide for a nominal 20% gross cost growth, specifying how costs could go up. One example would be if the contractor needed a big piece of equipment they were going to buy from somebody, and when they made the initial bid, the supplier said it was going to cost X dollars, but then when it came to time to buy it, the supplier says it was going to cost 1.1 times X. Then that would be a legitimate cost escalation thing, that 10% increase. That would eat into the difference between the 7.8 and the $9 million, but you're not going to exceed the $9 million. Well, Langley wasn't all that enthralled about this, as you might imagine. The first thing he had to do is, what does $7.8 million buy? In other words, they were talking initially about spending $9 million. Now they're going to spend 7.8 up front, and it's going to be allowed to grow to 9. Well, you still get a large test section. You still get the air and freon. We don't get into above atmospheric pressure testing. And the testing and the Mach number, instead of 1.2, it's going to be 1.15. Take a lot longer to handle the gas, to evacuate the test section, to exchange from freon to air. Research people say, well, even with these reductions, it's still worthwhile doing. So Langley revises their request for authorization and fires it off to Washington. But while this is going on, they start thinking about this thing. You know, we thought this job was going to take $9 million. Now we're saying we can do it for 7.8 by just cutting down a few things. Can we really do that? Langley looked at some other options to begin with, and looking at some other options. And finally, in February of 1953, they fire off a package to Washington headquarters, and they say, whoops, it is recommended that the conversion of the 19-foot pressure tunnel be canceled. You can imagine that got somebody's attention up there, right? The net effect was it put everything on hold for 3.5 months. Actually, cold hold for 3.5 months and partial hold for a lot longer. In the same paragraph, the first paragraph of this letter, this cover letter, they say, hey, this job is too important to be canceled. What you wizards need to do is go out and shake the trees and get the money so we can do the job properly. And look, we got a new estimate for you. not $9 million, it's $11.4 million. But don't worry, that includes the 20% escalation factor. Well, you can imagine how that flew, right? So they argue back and forth. They look at the escalation factor, they look at what's nice to have, what's absolutely necessary, what would be good to have, but if we don't get it now, we can add it on later, and that sort of stuff. Even John Stack got involved in going through the list of stuff. First, they start talking about 9.25 million. Then finally, they agree on a $9.6 million. This is really a little bit more increase than you might expect, because there's been some significant changes in this cost escalation factor. It's no longer 20% across the board. It doesn't apply to some things anymore, and some other things it applies. It's different from 20% and that sort of thing. So Langley fires off a revised RFA. I mean, of course, these are just all, this is all agreed to. They just send a piece of paper up that they're already meeting of the minds on, so obviously headquarters is going to buy it. And technically that RFA was approved in September of 1953. So everything is going along now. Getting back to staffing the job, start putting the drawings and specifications. Left here I have the major tasks. In the middle I have the contractors. And on the right I have the date the contract was awarded and what the price was. And this price is the capped price, not the starting price, the capped price. And as you might imagine, over the time of the job, all these contracts creeped up to that cap price, but they didn't, the total didn't exceed that 9.6 million. You see, the largest contract was with Pittsburgh Des Moines, which was the tunnel shell, the building addition, and whatever. A little over $1 million contracts for the electric motor, the freonization system, the test section, smaller contracts for the rotor blades, the fan blades. Langley initially was going to build the fan blades in-house, but they decided to do that out of house. And then the miscellaneous items like I mentioned before. All of these contracts were awarded on competitive bid except for the test section contract. When this job was put on hold, the technical services just couldn't let the engineers sit there on their hands, so they had to get the people, put the people on the other job. So when it looked like the job was going to be revived, they just couldn't go out and grab these people and put them back in. So they had to focus on what was the most important, they thought. So they focused on the general construction contract, and they didn't put much emphasis on the test section. So they petitioned NASA NAC at headquarters to let them award a sole source contract to the Newport Shipbuilding and Dry Dock Company for the design and fabrication of the test section. Here again, Langley would furnish the dimensions of the test section, but the shipyard would in effect design it, where the original plan Langley would have designed the test section and just had somebody build it for him. The reason the arguments put forth about going with the shipyard was, hey, it was close at hand. We can really keep tabs on these prices. You know, cost escalation was a big deal. They've done a lot of work with them before, so we have a good idea of what their costs really are. Headquarters bought this. So a contract was entered into the shipyard to build the test section, and what was called the auxiliary seals. They would be the big valves that would allow you to isolate the test section from the rest of the tunnel, so that you'd only have to evacuate 250,000 cubic feet of gas to make a model change, say, as opposed to 1 million cubic feet, which is the volume of the whole tunnel. The shipyard was going to design and erect this test section over at the shipyard in Newport to make sure everything fit together. NASA would go, NAC would go over and inspect it to make sure it was okay. Well, it turned out to be okay. Then after that inspection, then the shipyard would take it apart, the minimum amount, not the whole thing, a minimum amount, and ship it over to the site and Pittsburgh, Des Moines would put it in. Let's kind of look at the construction schedule. We've got years on. Don't take a straight edge now, put on these. When McGill first came up with this idea and sold it in the summer of 1951, he was thinking the whole job would take 36 months. And even at that, he was concerned about it being obsolete because all the problems were going to be at supersonic speed. The first RFA, we talked about 30 months. The engineering people figured it would take 900 days to do this job if the contracts could be all let in the appropriate sequence. And that 900 days would include the procurement cycle as well as the work period. 30 months. Well, we know that that's where the big hiccup came about the redefining what $9 million meant. So in what I've been talking about today, this is the third RFA. It's not really the third RFA, but the one where everything would start hopefully on July 1st, 1953, would be another 30 months. So the job would be finished sometime in this time period right here. Let's see what really happened. What happened was that the major contracts weren't issued in the proper sequence. They were issued when the drawings and specifications were ready. And the time period for the contract was the time it would take to do the work if the work was totally independent of all the other work. Well, you can see that that's not going to work. Here's the electric drive. This is Westinghouse contract, and they're going to have the motor about here. Okay, where's the motor going to go? It's going inside the cell. Who's building in the cell? Pittsburgh, Des Moines on the general construction contract. They don't even start work until a couple of weeks before the Westinghouse contract is scheduled to be completed. Now, how in the world are they going to put the motor in the cell? And the cell's not even going to exist. It's just be a figment of somebody's imagination. It's just going to be a little drawing on a cat's-off piece of paper. The same thing goes for the Freon system. It's got to go in a building. Pittsburgh, Des Moines is going to build a building. But the Freon contract is scheduled to be complete just a couple of weeks after the Pittsburgh, Des Moines. So this is not going to work, obviously. And the reason things worked out this way, they wanted to get that money obligated as quickly as they could. We government workers know about obligating money, right? So the first thing they've got to do is change the time on these contracts so they're in better lockstep. So if they go through 2 or 3 days, 58, 57, 58, and finally they zero in that, hey, look, it looks like we can get this job done by the summer of 1959. That's a long time, right? This idea was sold in the summer of 1951. We're talking about the job being done 8 years later. And McGill's talking about 3 years it's going to be obsolete. There's more than just getting these contracts in lockstep. It has some problems, too. Like there was a strike at the Westinghouse plant. One of Pittsburgh, Des Moines subcontractors went bankrupt. Plus, some of the work turned out to be a lot more difficult than anticipated, but it wasn't going to cost any more, fellas. It was going to cost that limit. So what we're talking about now is the summer of 1959 for everything to be complete except for the Freon system, and it wouldn't be totally complete till the spring of 1960. Now that doesn't mean that some aspects of the gas handling system wouldn't be complete, but the Freon capability wouldn't be complete until the spring of 1960. Okay, I'm going to show you now some pictures of the work in progress, so to speak. The first sign of any activity at the construction site was digging some trenches to run the new cables from the modified Back River substation to the new motor. Here's one of those trenches. You notice it's full of water. If you look at a lot of pictures of the construction from time to time, you see a lot of water in this area. The substation was part of the initial activity too. This guy I don't think was accomplishing much right here, but the substation work was really coupled in with some work that was being done with 8-foot tunnel also. But the first sign of activities at the construction site itself was associated with getting the electric power from the substation to the new motor, even though the new motor's not there yet. Remember I told you the diffuser had to be, existing diffuser had to be removed. Here the picture shows the diffuser's gone. This is the foundation of the building. This pedestal here forms the base for the what's called the Clark compressor now. Back then was a 5-stage compressor that was the heart of the Freon system. Here some of the diffuser sections, existing diffuser sections, stored on the shore back river over here. There's a spin tunnel in the background. This view shows some of the structural steel work for the building addition. Remember, it's going to be a 2-story addition. Here, another view showing the steel work associated with the building. You see some of the big cranes that were associated with this activity. This big concrete blob here is the foundation for the motor. The motor would go in a nacelle. That part of the tunnel where the nacelle goes has been removed here. And then the loads will be transferred down into this big concrete base. Here's a rotor arriving by barge. You can get an idea, it's mounted on a tractor trailer truck. Get an idea of how big that baby is by comparing it to the people standing on the deck of the barge. Here we see the nose of the nacelle. This is the thing this is geometry that Katzoff sketched out on a piece of paper. Here again you can notice how large this is by comparing to the people standing here. Here we're looking inside the plenum towards the big end, towards the southern chamber. Here's a portion of the test section that's being installed. Notice the test section has cropped corners. That was because of some high-intensity lighting could be mounted in these test sections, so we'd have high visibility, high-intensity lighting for high-speed photography. It also had another benefit. You're going from a circular entrance cone through a square test section out to a circular diffuser. Well, these cropped corners made the test section less square, so it helped a little bit in the transition of the flow through the test section. One thing I didn't mention about the design of the test section was they wanted a long test section, they wanted good flow over a long distance because aeroelastic models are a lot bigger than typical aerodynamic models. Here the rotary compressors, these are just compressors that just move large volumes of air. 6 of these, really 3 motors and 2 compressors attached to each. That's where there's no pipes installed yet, but this is where the big piping would be installed. This shows a part of the big 5-stage compressor, one of the stages right here. Okay, so the construction is proceeding along pretty good, but while the construction is going on, and some other events that were going on that might be, I think, of interest, and I want to point those out now. In September 1955, the Transonic Dynamics branch was formed, and Larry Lofton was appointed head of that branch, and McHugh was the assistant head. This branch was composed primarily of Lofton's general aerodynamics section and the remnants of McHugh's 19-foot pressure tunnel section. There wasn't much left of McHugh's section because the guys were scurrying off to other aerodynamic facilities. This branch was divided into 2 sections and a unit. A fellow named Norm Land headed the unit. Robert Boswinkle headed one of the sections, and our friend Bill Connor headed a section that was called the Transonic Dynamics Tunnel section. This is the first time those magic 3 words appear in Langley history. As part of this branch, Lofton now owned the 19-foot pressure tunnel, which was closed in October of '55. Of course, NASA was created in '58. Later in '58, Lofton moved over to the front office to become technical assistant to Floyd Thompson. So the Transonic Dynamics branch was renamed the Dynamics branch. Boswinkle, who had been one of the section heads, was appointed branch head, and Bill Connor became the assistant branch head. This branch had no internal organization, no sections or units or anything. But it was just this branch, renamed the Dynamics branch with new management, new top management. Okay, back to construction. As the year dawned for 1959, it was really becoming obvious now that, hey, this thing really probably is going to be finished sometime middle of the year. What are we going to do with the rascals? You know, this thing started out, we're going to test full-span, dynamically scaled aeroelastic models at transonic speeds of these new, complex, very flexible vehicles. That sounds wonderful. But that's not much meat on the bone. So a special committee was established in February of '59 to take a look what might the test program be of this new facility. It included people, most of the people on it were from the full-scale division: Boswinkle, Connor, Axel Matson, two people from Dynamic Loads. Joe Martin was one of those, one person from Flight. They came up with a shopping list of 10 things. I don't have 10 things on this list because I've combined some of the things here. But it ranged from some relatively simple models to complete airplane models. And the complete airplane models were going to, one of the objectives of those was to develop a means of supporting these dynamically scaled full-span models in the test session at transonic speed. The methods that were used at subsonic speeds weren't going to work very effectively at transonic speed. So helicopters, also some tests of a Pacific airplane, some novel things like sails. But the first tests that were going to be conducted were the flutter correlation tests, and we've got one of the test engineers in our audience today, Tom Fono. These models consisted of some sidewall-mounted models and some sting-mounted models. I think there were actually 3 series of tests. The planform and the planform shape and the dynamic characteristics were similar to some models that had already been tested in the 26-inch transonic blowdown tunnel. So this was the first test that, research test that were conducted in the tunnel. So we got the test program laid out. Let's see what's going to happen to the construction process. The motor first ran in February of 1959. This was just a motor. It wasn't hooked to anything. It wasn't hooked to the rotor. There were no fan blades. Later on, they hooked it up to the rotor and hooked up with one fan blade. I don't know how fast, and they call that sweeping the tunnel. I don't know if they were trying to blow the dirt out of it or what. By midsummer, most of the work had been completed, not all. There were a few things hanging fire. Of course, the freonization system was still hanging fire because that wasn't going to be completed until early the next year, remember. Pittsburgh Des Moines hadn't quite finished all their tasks. But the NASA, we're back to NASA now, we saw NACA, now it's NASA, said, okay, Pittsburgh Des Moines, we'll accept everything you've done so far. We're not going to let you off the hook for the stuff that needs to be done. But if you'll let us use what you've done so far, we won't hold your feet to the fire as far as when you complete these other tasks, and we won't assess any liquidated damages of $100 a day. A lot of these contractors got assessed liquidated damages of $100 a day because they were behind the established schedule. So Pittsburgh Des Moines, I mean, obviously it's great, why not? So acceptance and checkout tests ran from August to December of 1959. NASA essentially bought off on the motor and the drive system in early November. The motor came with a 1-year guarantee. First time the tunnel was operated under NASA control was the 1st of December 1959. Heretofore, the contractors have been operating everything. The tunnel was calibrated for use in air in January of 1960. And the first research test, which was test number 2, the air calibration test was test number 1, was in February 1960, and this was the first time a flutter point was obtained in the tunnel. Also, it was the first time the tunnel was operated from the control room. Heretofore, the electrician had operated the tunnel in the electrical control room and communicated back and forth to the test personnel in the control room. The modus operandi in the future would be the electrician would bring the tunnel online low speed and transfer control to a technician in the control room. The technician in the control room would control the tunnel during the research operations and slow it down, transfer control back to the electrician in the EE room, and take the thing offline. The Freon system was finally got ready, was checked out in March 1960. The Freon tunnel was calibrated for Freon operations from April to the beginning of May 1960. So somewhere in here is the birthday of the TDT. I would say it looks like it's May 2nd, 1960. That's the first time everything essentially was finished. First time the tunnel was been calibrated in air and been calibrated in Freon, so it could be used for any of the purposes that it was intended initially. So happy birthday, TDT, I guess. This is what the final product looked like. If you remember what the 19-foot tunnel looked like, it looks a lot like it. Except we've got now a 2-story building. We've got a cooling tower in the courtyard. We've got a 34-foot extension here. And the new tunnel has some expansion rings back here that the other one didn't have. This piping on top here is associated with the gas handling system. Air comes in the top, Freon comes in the bottom. A couple little things about this. Although the tunnel was supposedly designed from 1.15, if you hold your mouth right and the wind's blowing from the right direction and everything, you can actually squeeze it up to 1.2. But the test section was designed for 1.3. So you should be able to increase the Mach number to 1.3 without doing any modifications to the test section, say by adding auxiliary suction or something like that. Now, I mean, somebody would have to check that out, but that would be the notion. So it had a little bit, in terms of Mach number, it had a little bit higher capability than anticipated. Also, the motor was designed in such a way that the horsepower could be increased in a straightforward way, which it was in the 1980s. So that's how the TDT came into being. There's one other little thing I'd like to mention for some of you might find of interest. In the summer of 1961, there were 2 seats of air elasticity at Langley. We started out authors for gear, vibration, and flutter branch. Now we've got the dynamics branch and the full-scale research division. There's another seat of air elasticity. This is a 19-foot tunnel, Transonic Dynamics Tunnel, but it's also, the people working here had developed a flutter capability by using a 26-inch transonic blowdown tunnel. So they were competing organizations in terms of experimental air elasticity at Langley. And the relationships weren't necessarily all that friendly. There was a certain amount of competition between these things. At this point in time, our friend Larry Lofton now is no longer a technical assistant to Floyd Thompson. He is one of the Langley assistant directors. John Duberg, not Duberg, I can't think of the guy's name. The division chief, anyway, when all this stuff started, was also now assistant director. Lofton didn't think it made too much sense to have these 2 different branches and 2 different divisions, both addressing experimental air elasticity. So he, in effect, caused the dynamics branch to be transferred to the dynamic loads division in the fall of 1961. So now it means you've got 2 branches in the same division. Before you had 2 branches in 2 different divisions, now you got 2 branches in the same division. Lofton didn't like that either. He didn't think that was a good idea either. So in January of 1962, he caused the dynamics branch to be renamed the aeroelasticity branch. This is when the aeroelasticity branch was first created. And the aeroelasticity branch was composed of everybody within the dynamics branch and the TDT, plus that portion of the vibration and flutter branch that was involved with experimental aeroelasticity. There was 8 people involved. So the size of the dynamics branch was increased by 8 people. Bill Connor was moved from assistant branch head to assistant branch head of the structural dynamics branch. Connor developed a reputation now, somewhat of a hardware guy, the kind of guy who could get things done, make things happen. And they were in the process of getting a new research lab, centrifuge and all that sort of stuff. So he seemed to be the guy who would put him over there, and he was going to shotgun that job. And a guy by the name of Jerry Rainey, who came from the vibration and flutter branch, he was actually a section head, was one of the 8 people, and he became Boswinkle's assistant branch head. So that includes the tale. I hope you enjoyed it.
Does anybody have questions? Okay, thanks.
Thank you, Bob.
Well, I appreciate you coming.
Launch vehicles, and Bob's fairly renowned in that area with regard to Buffett work that he's done for launch vehicles as well as for fixed-wing aircraft also. From that point on, though, he was pretty much involved in a hybrid mix of anything that flies. And Bob's been very influential with regard to experimental studies as well as impacting what was done with analysis studies throughout the years in aeroelasticity. And few people have the breadth of aeroelastic research experiences that he has. While in the aeroelasticity branch, he served as head of the Flutter section, then became leader of the Flutter group. And this was after Don Harris got rid of section heads in the research organizations in 1977. And then in January 1981, he began a 7-year tenure as head of the configuration aeroelasticity branch, formerly the aeroelasticity branch, and now currently, after dividing into several different aeroelasticity branches in that time period, is recombined in today's aeroelasticity branch again. At this point, I'd just like to say, and Bob, I've shared this with Bob in the past, but only with Bob, and I've never said it in public, but I came into the aeroelasticity branch not too long after he became a branch head. I co-opted before he was branch head in 1980, and then I came in 1982 as a permanent employee. And Bob Doggett is very much, as I have worded in the past, the father of my career. And so I have a special relationship with both him and the TDT, and very much appreciate what he's contributed to my career. In 1988, he spent a brief period as chief scientist of the Loads and Aeroelasticity Division, and then for about a year as chief scientist of the Structural Dynamics Division until he became assistant chief of that division in July of 1989. Appreciate you coming out today. I'm Stan Cole. I'm head of the aeroelasticity branch. Many of you I recognize out there, so a lot of you know me. But I'm going to take just a moment to introduce Bob to you also. You can see from his chart here that his name is Robert V. Doggett, Jr., but he goes by Bob. And a lot of you also know Bob, but maybe you don't know very much about his career, and so I'm going to cover just a few things before he talks today. First of all, he's a native of Richmond, Virginia. Came to work at NACA's Langley laboratory immediately following his graduation from Randolph-Macon back in 1957. He was initially assigned to Charlie Watkins' analysis section in the Dynamic Loads Division, but he never actually worked there. By happenstance that Bob describes himself as good fortune, he ended up going to work in Joe Martin's Flutter project section, and there he began to work with aeroelasticity, even though at the time he didn't really know what that meant. And probably a lot of us that have worked in the field can say something similar to that in terms of the beginnings of our career. His initial work involved Flutter model testing in a number of different wind tunnels and also some analytical studies. Work ranged from simple research studies to more complex investigations of full-scale designs. In January of '62, he was reassigned to the newly formed aeroelasticity branch, which was still in the Dynamic Loads division. And this began his association with the Transonic Dynamics Tunnel that he will talk to you about today. And this was a relationship that either directly or indirectly remained there throughout his career, his relationship with the TDT. At the time of this transfer, the focus of his work was shifting away from airplanes and toward line. In October 1994, he became Special Assistant to the Chief of the Structures Division. He retired in March of 1995, and for the last several years has continued to work with the Aeroelasticity branch as a Distinguished Research Associate, primarily serving as an archivist for our Aeroelasticity archive, our library, and that also is very much appreciated in terms of his continued contribution. He's published many technical papers, made many technical presentations. He is actually co-holder of 2 patents that resulted from his research, and as I've already said, he's known throughout the world for his contributions to aeroelasticity. His accomplishments were recognized by a number of group and individual awards throughout the years, including the NASA Exceptional Service Medal and the Director's Award from the Army's Aerostructures Directorate. And I should have started probably with just a word about this presentation. He made this presentation to the Aerospace Flutter and Dynamics Council, as is stated here, just a few weeks ago, I guess. And that was both the presentation and the council meeting here at Langley was planned to be held in conjunction with the 50th celebration of the TDT. And a number of folks were quite impressed with the information that he brought in this presentation. And so not only is he presenting it to you today, but we're also trying to capture this on video today so that we'll sort of have the story, if you will. So with that, Bob.
Well, I appreciate y'all coming today. I see a lot of people have familiar faces, but since this is going to be videotaped for posterity, I thought we might step back a little bit and talk about aeroelasticity. When I gave this talk initially for the Aerospace Flutter and Dynamics Council, I was speaking to friendlies, and they knew what I was talking about. They knew what aeroelasticity was and that sort of thing. But perhaps there's somebody here that doesn't know, but when perhaps somebody look at the videotape in the future, they might not know either. I don't know. This is high tech for me. I'm a more physical pointer guy. Aeroelasticity exists because flight vehicles are flexible. There's a reciprocal relationship between load and deformation. Take an airplane wing, as it flies along, it will deform due to the aerodynamic load. The new shape will change the load, and eventually some type of equilibrium condition will be reached, or an instability will occur. There are three types of forces that are involved in aeroelastic phenomena. They're the structural inertia, elastic, and aerodynamic forces. Strength doesn't have anything to do with any of this stuff we're talking about. It's stiffness. And how these three forces combine, how these three forces combine together determine whether it's going to be a static phenomena or a dynamic phenomena. If the elastic forces and the aero forces combine, then it'll be a static phenomenon. An example of a static phenomena is aileron reversal. In other words, the shape of the wing will change such that the ailerons act in the opposite sense. So when the pilot wants to roll to the right, the plane goes to the left. There was a famous airplane that had a problem with that, and that was the Japanese Zero during the Second World War. It didn't suffer from aileron reversal 100%, but it suffered from a big loss in aileron effectiveness. And the tactic was to get it into a high-speed dive and then pull away. If the Zero was on your tail, then he couldn't turn as fast as you, and he tried to roll he couldn't roll as well as the American planes. Dynamic phenomena is something like flutter. Flutter is a vibratory thing, a combination of all three of these forces. Air elasticity is perceived as evil. It's not a good thing. It can't be allowed to happen. You can't let airplane wings flutter. You can't let airplanes have aileron reversal. You can't let the buffeting be too severe. So these things have to be designed out of airplanes. If an airplane or a helicopter or a launch vehicle or whatever it may be has an air elastic phenomena, to fix it generally you have to add stiffness. When you add stiffness, you add weight or mass. When you add weight or mass, you penalize the performance of the vehicle in one way or another. Less payload, more fuel consumption, shorter range, or whatever. Now, it's not always evil. Whoops. It's going to take me a while to get used to this, I think. The Wright brothers used aeroelastic principles in the lateral control of their flyer by changing the shape of the wings, put on those cables. They didn't know, the word aeroelasticity hadn't been coined. It wasn't coined until the 1930s by the British. Recently, there's been a lot of work focusing on how can we use these deformations in a good way. So maybe aeroelasticity is becoming less evil, but it's perceived generally to be bad. Okay, as Stan mentioned, I initially gave this presentation to the Aerospace Flutter Dynamics Council several weeks ago. And what I'm going to be talking about is how the TDT came into being. And what I'm going to do is I'm going to talk about how the original notion arose, and I'm going to follow the story through the selling of the idea, how funding was acquired, design and construction, and some bumps along the road. And there were some big bumps along the road, and then leading to the finished product. And also I'll mention some related